Hello everyone, myself Shruti. This is a scholar from the ID University. Uh, I'm very thankful to International Research Awards on High Energy Physics and Computational Science to giving me an opportunity to present my paper on parametric analysis of dust and acoustic waves in superthermal plasmas through non-autonomous KTV framework. I'm pursuing a PhD under the supervision of Dr. Naresh Mohan Chadha. So this is the outline of my work. First, we will study the introduction. Then I'll give the example of linear and nonlinear partial differential equations. Then I will introduce the damped force KdV equation with some examples. Next, we will study the visible range of parameters regarding with this damped force KdV equation. Then we will study the bifurcation analysis, then conclusion and correspondingly references. So, in the introduction, as my equation is related to the nonlinear partial differential equation, which is basically used to model many physical systems. For examples in fluid dynamics, plasma physics, solid mechanics, quantum field theory, heat and mass transfer, signal processing, and combustion problems. So these nonlinear partial differential equation consist some analytical solutions which can be generalized to describe a broader class of systems or phenomena. This generalization is particularly useful when studying variations or extensions of a particular model, which allows the researchers to apply their understanding to different scenarios. On the basis of these analytical solutions and some parameters which this equation consists, we will do the bifurcation analysis, which is a mathematical analytical approach to use to study the qualitative behavior of a dynamical system as the parameter varied. So our main focus is on to study the dust and acoustic waves, which are basically low frequency electrostatic waves in a collisionless dusty plasma, which consist dust particles and ions. In this construction, we will generate the model equation with the help of some major governing equation. Then we'll apply the reduction perturbation techniques, which is basically depends upon some stretching variables. By using these variables, we can generate a model which is damped force KdV equation. So, firstly, we will study the advection diffusion equation, which is basically the base of the damped force KdV equation. This is an example of advection diffusion, which is a linear partial differential equation in which the second term represents the advection term, and the third term represents the diffusion term. This equation is basically advection dominated because epsilon is very smaller than a. And in this equation, we have found that the central differencing numerical method will fail. So based on that advection diffusion equation, I have generated the damped force KdV equation by using the previously governing equations and reduction perturbation techniques. So this is my damped force KdV equation, in which the second term represents the advection term, and correspondingly A represents the nonlinear coefficient, and the third term represents the dispersion term, and correspondingly B is a linear dispersion coefficient, and fourth term is C phi, which is representing the damping term, and C is the damping coefficient, and the fifth term is a forcing term, and B is a forcing coefficient, in which S2 is the source term. So by solving this damped force KdV equation with the help of some analytical methods, we can generate the analytical wave solution, which is given here. This analytical solution is directly depends upon some parameters, which you can see that F naught omega and A, B, C, which are related to the damped force KdV equations. So the interesting fact in this equation is that these parameters, we can say them as a variable coefficients, are further depends on other parameters, which are mu and kappa. And the overall analytical system will further depend upon the 5 parameters, which are mu, kappa, nu ID0, which is a damping coefficient, omega, which is a frequency parameter, and F naught is a forcing parameter. So it may be interesting to see the effect of the range of these parameters. In the literature, I have seen that many researchers have studied with respect to the constant values of these parameters. But in my work, I have focused on the range, focused on to study the range of the effect of these parameters. So in this diagram, I have tried to make some four feasible range for these two parameters, which are basically mu and kappa. And with respect to these range, we will see how the soliton behave. So for the first figure represent the first range. So for the first figure, we have seen that there is a structure of soliton like of Gaussian pulse structure. And in the second figure, which will be drawn for the reasons, which is drawn for the reason second, represent the refractive behavior. In the third reason, you can see the amplitude of the soliton is approaches towards 10 to the power 14 value, which is unexpected. And the fourth one is the for the fourth reason in which our soliton breaks. So next we have additional parameters in our soliton, in which first one is the nu idea 0, which is a damping parameter. You can see for a range of increasing value of damping, the back end side of the solitons will show the compressive behavior, and for a higher value of the damping, this soliton will compress forever. Next is the impact of forcing term in the frequency. You can see for the forcing term, for increasing value of force, you can see the clear for increasing value of forcing term, the back end side of the soliton will rise apparently, and for the increasing value of frequency, there is an oscillation in the soliton. So after investigating the effect of the parameter on the solitons, we are moving towards the bifurcation analysis, which is just a qualitative change in standard in dynamics produced by varying parameters. So basically, tools of bifurcations are phase portraits, time series plots, Lipnov exponents, and d-infinity parameters. So Lipnov exponents are basically used to recognize the cues in the system, whether there exist a cues in the system or not. So in this for this we will follow the basic theory of bifurcation, and we will generate the Lipnov exponent. If we'll get any positive value of the Lipnov exponent, then we can say that there may be a cues in the system, which depends on the initial condition. So what is chaos? Chaos is a aperiodic long-time behavior deterministic dynamical system that exhibits a sensitive dependency on the initial condition. And how can we determine that it is a chaos, which is basically depend upon the positive value of the Lipnov exponent. So next is our d-infinity parameter, which is again a tool of bifurcation analysis, which is the largest Lipnov exponent value, which represents a rate of divergence of two closed trajectories, which quantify the effect of a stretching phenomena in the chaotic system. So what we are doing in bifurcation analysis, what are the basic procedure of the bifurcation analysis is that First, we take a partial differential equation, then we'll apply the some transformation on it and convert it into the ordinary differential equations. By using this ordinary differential equation, you can see the ordinary differential equation. So in this case, we move towards that what will happen when there is no damping, there is no forcing term in it, and when the damping and forcing both are not present in this system. So on that basis, we are moving towards some cases depends on these situations. In this first cases, we are considered here that when damping them and forcing them both are not present. In that case, we will approach it. We have this ordinary differential equation, so which is an integrable system. So by integrating the system, we have generated the dynamical system, which is a two-dimensional dynamical system. By solving this dynamical system, we can get some solution sets, or we can say two equilibrium points. And with respect to this equilibrium point, we can justify the nature of the trajectories around this equilibrium point, which depends upon the nature of the coefficient matrix, which is given here, which is saddle and center. So on the basis of those equilibrium points, I'm going to represent the QR plots with respect to both region in which the behavior is stable and unstable, both shows here. So you can see there is a stable center. Stable center, for pointing out the stable center, you can see the spiral behavior of the trajectories around the stable point, or you can say around the first equilibrium point, or whether it will be second equilibrium point. So by seeing the spiral trajectories, you can mention that this is a stable center, and by seeing the opposite direction of the direction fields, you can see that you can say that that point is saddle point. And similar the opposite behavior we can manage, we can see in the with respect to the reason second. So as I have already told that our main focus is on to study the impact of the range of these parameters. So these are the phase portraits which are representing the range of the parameters kappa and correspondingly mu. You can see the effect for the range of the parameters by with the figure D and E. Similarly, we can see the impact of mu with the figure D and E. There is a break in the trajectories for increasing value, and there is a redevelopment of the redevelopment of the trajectories with respect to the increasing value. So our next case is when we choose there is no damping term but forcing term is present here. With respect to the forcing term, here forcing term can be considered as a perturbation term additionally required. So this equation is again a integrable equation. By integrating this equation, we can get the dynamical system in two dimension. Since this forcing term is a perturbation, so basically the solution sets, or you can say the equilibrium points with respect to this dynamical system, will be same as in the case first. So in this case, we have two additional parameters. First one is the forcing parameter F naught. Next one is the frequency parameter, which is omega. So we'll see the impact of the range of these parameters. So these are the phase portraits which are indicating the chaotic attractor for the increasing value of forcing parameter and the for the increasing value of omega parameter. So we have justified our results with the help of d infinity parameter, which you can obviously see the oscillations in the waves and the unpredictable behavior of the waves for increasing value of this omega and omega, the frequency parameter, and forcing parameter. Our next case is when damping term is not present. When damping term is present and forcing term is not present. In that case, we'll get a three-dimensional dynamical system whose analytical point will be 0, 0, 0, and the major bifurcation parameter for this system will be the damping parameter. So this is the effect of the damping parameter for increasing value of damping. You can see that for increasing value of damping, there exists a cues in the system. So this is the time series plots. You can say the Lipnum exponent plots. With the help of these plots represents the two cases when damping term is present in the system and forcing term is absent, and when both terms are present. So you can see that with the help of this positive value of Lipnum exponent, there may be a cues in the system. So in the overall study, we have studied the fact of the different kinds of parameters like mu, kappa, which are basically related to the nonlinear coefficient, dispersion coefficient, damping term, which is a damping coefficient related, and the forcing term, which have two parameters, which are forcing parameter and the frequency parameter. So these are the wave propagation. You can see with respect to these three cases, the periodic and the chaotic behavior with respect to these parameters. So this is the references. Thank you so much.